Hi folks, in this video, I'm going to show you how to perform a mixed factorial ANOVA using JASP. First open up JASP. Once JASP opens, go to Show Main Menu, Open, Data Library, and ANOVA. We're going to go ahead and select one that says Mixed Design ANOVA, so bugs would be appropriate here. Get oriented with the dataset. Here you can see that we have a categorical variable of gender. We have a high and low value for repeated measures components, right? Low D, low F, low D, high F, high D, low F, high D, high F. So these are four different conditions for our dependent variable, which represents our repeated measures component. To perform the ANOVA, go to ANOVA, go to repeated measures ANOVA, and we're going to make sure that we have each of the four conditions represented. To do this, under the repeated measures factor, type in level 3 and level 4. Go ahead and move the repeated measures components over to the repeated measures box, and then take your gender as your independent variable and move it to the between subjects box. Now we have our output here, but before we do, let's make sure that we select descriptive statistics. Let's check for our basic assumptions of sphericity and homogeneity. Let's make sure we have greenhouse geyser in case the sphericity assumption is violated. And let's make sure we have our post-hocs in place. So when we run post-hocs, we need to make sure that we have it for both the repeated measures component, the independent groups component, and the independent and repeated measures interaction component. Let's make sure we're Bonferroni corrected and our confidence intervals are set to 95%. Okay, let's go through this in turn. So because we have a mixed factorial ANOVA, the first thing that we need to think about with all this data is let's start with something that we know. And that would be looking at the descriptive statistics. So level 1, level 2, level 3, and level 4, each of those represents one of the four levels for the repeated measures variable of interest. And then for the gender variable, we have two possible levels in this case, females and males. And so this would be a 4x2 mixed factorial ANOVA. You can see that for level 1, the female mean and standard deviation has 58 participants, 5.897 is the mean, and 2.745 is the standard deviation. For males, it's 29 participants, 5.103 mean, and 2.508 standard deviation. This is done for each of the levels of the repeated measures independent variable. So we have our means, we have our standard deviations, and we have these data for both levels of our independent variable. Very, very important. Okay, let's go ahead and check for our assumptions. So the thing we need to check for with a basic assumption of homogeneity of the variance is we want to make sure that the p-values in all of these cases are larger than 0.05, which tells us whether or not the variance of each of the means and standard deviations are statistically different from each other. And we can see that because all of the p's are larger than 0.05, we meet the basic assumption for Levene's. To check for the basic assumption of sphericity, we would look at the p-value under sphericity to determine the same aspect for our repeated measures independent variable. And unfortunately, we see that we have violated the basic assumption for sphericity because the p-value is smaller than 0.05. So this tells us that for each of the levels that there is statistically different variances for each of the repeated measures variables that we have, and we may not be able to use them as such. So we'll go ahead and make sure that we use the greenhouse geysers line when correcting for that in our analysis. So let's go ahead and jump up now to the repeated measures ANOVA, and you can see that for the repeated measures question, so when we're only assessing is there a statistically significant difference between the conditions regardless of sex, you can see that the greenhouse geyser line, which is how we're correcting for that violated assumption of sphericity, we have a sum of squares value of 201.047. We have a degree of freedom of 2.641. We have a mean square of 76.127. These processes, just like the repeated measures ANOVA, is exactly the same. We take the amount of variance that is explainable by the repeated measures component, divide it by its degrees of freedom, and you get the mean square. You do the exact same thing for the interaction, which accounts for not only the repeated measures component, but it also accounts for the interaction of gender as a second independent group's independent variable. And so when looking at the greenhouse geyser line, you can see that 21.082 sum of squares is attributable to an interaction between gender and the repeated measures factor divided by its degrees of freedom of 2.641. and you get mean square of 7.983. So when you do the residuals, this is what's left over for the sum of squares. And you can see that exploring the greenhouse geyser line, there's 962.095 sum of squares left out of the entire model. Dividing by its degrees of freedom, you get 224.480. And taking the sum of squares divided by its degrees of freedom, you get 4.286. So to determine the F statistics, you would take the greenhouse geyser's mean square of 76.127 and divide it by the greenhouse geyser of 4.286, and you would get your 17.762. To look at your repeated measures by your gender interaction term for greenhouse geyser, you would take 7.983 divided by the 4.286 of unexplained, and you would get an F of 1.863. Looking at the p-values, you would see once again that we have significant condition effects for the repeated measures component, but we do not have a significant interaction, which means that your gender and the condition to which you're exposed does not appear to cause a statistically significant difference in the dependent variable of interest. So because we have a significant repeated measures ANOVA and not a significant mixed factorial ANOVA, we could scroll down to the post hocs and only explore the difference for those post hocs for the repeated measures factor. And very similar, you can see that level 1 versus level 2, level 1 versus level 3, and level 1 versus level 4. These are all statistically significant because the p-value is smaller than 0.05. But when we compare things like level 2 versus level 3 or level 2 versus level 4, we see that there's not a significant difference in the dependent variable for those conditions. So something with level 1 appears to be driving this finding in this case. But we also see that to a lesser extent, there's level 3 and level 4. They're also statistically significant. So importantly, whereas the ANOVA told us that the p-value was smaller than 0.05, it didn't tell us where those significant differences lied, and so we ran the post hocs in order to do so. Also, if you were to look at the post hoc for gender, which we don't really have a reason to do because our interaction was non-significant, you can see if you were to take the data overall, the aggregate data for all 4 levels for females and all 4 levels for males, that there's no statistically significant difference in those findings. This is evidenced by the p-value being larger than 0.05. And then finally, because we did not have a significant mixed factorial ANOVA, independent groups by repeated measures interaction, we do not need to perform this post hoc, but we ran it because we didn't know if the findings were going to be significant at all. But if they were, we would be able to explore these p-values and you would be able to determine if there was a statistically significant difference by group, by condition in that case. So I hope this video was helpful. We'll see you all in the next one.